Hi, my name is Francisco Martin Rico and I will present our work PlanSys2, a planning system framework for ROS2. This work describes ROS2 planning system, also known as PlanSys2. It is a framework that lets robots execute plans calculated using a PDDL plan solver. In the 2 years of life, this framework is currently the reference in symbolic planning in ROS2, the new version of the standard in robotics programming ROS. PlanSys2 has been designed with robustness and efficiency in mind, and it supports multi-robot execution, among many other new features. In the last years, artificial intelligence and robotics have converged again after years of separate ways. In the awakening of modern artificial intelligence, these two worlds worked together. In these golden days, artificial intelligence produced many successful languages, like Lisp, Scripts, and Prolog. When the AI winter came, some roboticists like Rodney Brooks defended another way to create intelligent robots without a complete symbolic reasoning systems. The last decade has been fascinating because ROS fostered a significant advance in robotics by producing a vast amount of software that can be shared and integrated into different systems with guaranteed interoperability. ROSPlan was a successful package that let use symbolic planning again in robotics, integrated into layered architectures. ROS2 appeared as the new version of ROS in the last years, providing many features demanded by researchers and industry, and there is where we are. As we said, ROSPlan was the first successful package for symbolic planning in ROS, and it has been the inspiration for creating PlanSys2. For years, we have used ROSPlan integrated into our cognitive architectures. When we moved to ROS2 a couple of years ago, we confirmed that the ROSPlan developers were not interested in migrating to this new version. Then, we see an opportunity to develop a new system, with the learned lesson of using it, but for ROS2. PlanSys2 is an entirely new implementation, focusing on the weakness we detected in ROSPlan: efficiency, robustness, and usability. The design of PlanSys2 is divided into 4 main pillars. First, our systems should be reliable, secure, and predictable. By using the new feature of ROS2, we achieve these goals. ROS2 has a communication layer based on DDS, which provides real-time communication with different quality of service and security capabilities. Lifecycle Node made our software more predictable, as the main components implement an finite state machine with clear responsibilities in each life state. PlanSys2 architecture is modular. Each module is in charge of part of the functionality, being replaceable for adapting to particular needs. PlanSys2 can use several PDDL plan solvers, provided as plugins selected at runtime. Currently, we support OPF, temporal fast downward, and optics. An application that uses PlanSys2 must provide a PDDL domain and implement every action in this domain, called action performers. The application is also in charge of setting the initial knowledge, setting goals, and asking the PlanSys2 executor to run a plan. We made a great effort to facilitate the interface to the different modules, providing client libraries that hide all the complexity of ROS2 communication and knowledge management. As ROS2 nodes can discover and interoperate with other nodes in another robot, we have designed a way to request the execution of action in different robots. We can deploy more than one action performer for each action in different robots. The first action performer replying to an execution request will be in charge of executing the action. We can also set up an action performer to execute action with specific arguments. In this way, navigation action deployed in several robots needs that one argument is its robot ID. We could also have different implementation for manipulation action, specialized in manipulating one type of objects. The last pillar of our design is efficiency and robustness. We analyze plans to detect the action that can be parallelized, improving the completion time of the entire plan. We also optimized the reactivity of the action performer since the executor delivers one action to be executed. We also implemented many ways to monitor what is happening inside PlanSys2. Each module continuously notifies any change in its state, and the executor actor always publishes helpful debugging information. We are working on more applications to show this info and tools to analyze execution graphically. Regarding the PlanSys2 implementation, we also contribute to the planning system state-of-the-art in 4 aspects. First of all, we provide a novel way to execute plans based on behavior trees, run inside the executor component. When the PDDL solver creates a plan, it is analyzed to encode it as a behavior tree. Here we can see a plan produced by a PDDL plan solver, and here the resulting behavior tree. This behavior tree encodes parallel branches that can be executed simultaneously. Action can't be executed until the action depends on complete, and the behavior tree encodes these requirements. Each action in the behavior tree is a subtree that contains all the elements of a single action execution: the requirement checking, the application of the effects, and the real execution of the action, which control the external execution at the action performers. This subtree can be customized to include quality of service capabilities, debugging nodes, or any other particular element of a specific project. The behavior tree running at the executor produces requests to the real execution of action carried out by the action performers. Instead of using ROS to action, we designed a protocol in which the actions are auctioned. It fits with its specialized arguments. Available action performer of the requested action take part in this auction. This protocol uses the same channel. This is the same topic. An example is shown in this figure. When the executor has to execute one of the plan action, in this case the move action with the argument shown, it sends a request to all the action performers. Some of them reply, assigning the execution to the first and notifying the rest to free their commit with this auction. We also develop software components and libraries to facilitate the implementation of the action performers. Action performers can be implemented entirely in C++ or providing a behavior tree that encodes what these actions will do. We also provide classes to facilitate the implementation of ROS 2 action clients to other subsystems. This is useful, for example, to use nav2 or move it from these actions. Sometimes graphical interfaces are not very responsive or are very complex if it provides much functionality. This happened to us with the graphical user interface of the ROS plan. In PlanSys2, we provide a program called PlanSys2 Terminal. This is a command line program used to communicate with the different PlanSys2 elements in an efficient way. With this terminal, we can check the domain, make queries to this domain, or the knowledge in the problem expert. We can add or remove instances and predicates, request plans, or request a plan execution. In this video, we can see an example of a real session with the terminal. In this paper, we provide an evaluation of PlanSys2. Our research question is PlanSys2 robust and efficient enough to be applied with reliability in a group of real robots? To answer this question, we will use the next metrics. The first one is execution time and the number of plan and action executed. This will indicate the robustness of our system. It will be the amount of time that the system has been running interruptedly, generating plans and executing action. The second metric is efficiency. This metric refers to the percentage of time running action in PlanSys2 for the total execution time. It will give us a metric of the efficiency and reactivity of PlanSys2. The last dotted matrix is the failures and replanning. It will measure how many times the system has not been able to continue its execution by internal errors. We also provide the value of replannings, that it's a healthy value, because it will show that our system is able to readapt to new situations. We have carried out two examples in the same scenario. We will simulate the execution in several robots for the first experiment, and the second is the executing in a single real robot. The scenario is a kitchen where the robot must cook menus of 2 plates, randomly selected between 3 options, each one with different ingredients. The robot should navigate to different positions to take the ingredients. The robot can also run out of battery, making the plan fail and replan to fair reshares in the reshare zone. For this experiment, we will use 3 robots, each with an action performer for every action in the domain: move, transport, cook, and research. We made independent trial for 1, 2, and 3 robots. Each trial was about a couple of hours. For one robot, in these 2 hours, we successfully completed 76 plans with 9 replannings. We cooked 154 dishes and a total of 1,000 actions. There were no fails in the system during this experiment. With 2 robots, we increased the efficiency, cooking 203 using 1,550 actions. 100 of plans were complete in this time. We increased this number with 3 robots and with no internal error too. Next, we will show the execution of the real robot experiment in a professional robot, the Tiago robot from Power Robotics. As the robot has no manipulation capabilities, this capability is simulated with a fixed time waiting. For navigation, we use Navigation2 framework. The instructions to reproduce these are in this public repository. The video is a portion of the total experiment. We ran it for 2 hours with these results, showing the robustness and efficiency of our system. Well, we have presented the PlanSys2 framework, the reference package for symbolic planning in ROS2. This framework is available as binaries in the Eloquent, Foxy, and Galactic ROS2 distributions. The sources are freely available in GitHub, where we are building a small community. As far as I know, PlanSys2 is being used by the US Navy, the French company Safran, and recently the people of the Horizon Europe project Acroba communicated me their intention to use it. PlanSys2 also has a web page with description and tutorials. We hope you enjoy this video, and any comment or collaboration are welcome. Thank you.